Welcome. This short little tutorial is about how to do instrumentation with Omnitrace. There are two modes of instrumentation with Omnitrace, a binary rewrite mode and runtime instrumentation. So the difference between the two, I'm going to demonstrate using the nm tool, which lists the symbols for object files. And in particular, I'm going to look at the symbols that are in the text section and the symbols that are undefined. So let's run nm on this parallel overhead example. Okay, you can see from the list of the symbols that there's various different types of symbols. Their types are listed in this second column here, and then the name of the symbol. So we want to look at the text and the undefined symbols. Okay, as you can see, we have this Fibonacci function in the text section, a run function in the text section, several standard library functions that are undefined, a few templates that are instantiated in the text section, and several functions starting with an underscore, which are just sort of always there and automatically added by the compiler, in addition to some undefined symbols from the C library, like a memcopy, printf, and this pthread barrier functions. So in runtime instrumentation mode, effectively all of these symbols and more are available to be instrumented. In binary rewrite mode, the only functions that are available to you for instrumentation are the ones in the text section. Now, generally, the functions defined in the text section are the functions that you have written that are pertinent to your application. So a binary rewrite is actually a good way to limit the scope of what is profiled to your specific code, as opposed to instrumenting, say, a function that's defined in the standard library that you really don't have too much control over in terms of optimization. So I generally recommend going with the binary rewrite mode as a quick way to profile what's going on in your application. And then you can use the runtime instrumentation if you are concerned that what is actually slowing down your code is the standard library implementations defined in another library that you are using. So I'm going to print the available functions in binary rewrite mode. We're just going to call this a.inst for the parallel overhead. Now, watch the number of available functions for instrumentation when we have this -o flag. Okay. Now, if we remove the -o flag, this enables runtime instrumentation, which enables Omnitrace to instrument the functions that are undefined in the binary because they are loaded at runtime, and we're doing our instrumentation at runtime. So those symbols are available to us for instrumentation. And as you can see, because we're doing instrumentation at runtime and we have all those extra symbols, the instrumentation takes quite a bit longer. Okay, looking at this output, you can see that as opposed to when we did the binary rewrite, the only functions that were available for instrumentation were the ones that were defined in our parallel overhead.cpp file and just the parallel overhead module. But when we did runtime instrumentation, you see we have all these extra modules that are available to us. As you can see, this goes on quite a bit. These come from the libraries that are linked in to the parallel overhead executable. So let's take this same example, the examples parallel overhead, and let's run Omnitrace, and let's set the verbosity to -1 to suppress a bunch of the output. And let's pass the simulate flag, and then let's ask it to print the available functions. We use the -- to separate any arguments for Omnitrace to the executable, and if this has any arguments. Here, this double hyphen basically gives you differentiation. And I'm going to add the -o flag, which specifies that we want to do a binary rewrite. Okay, so we can see from simulating the instrumentation, we asked it to print the available functions. As you can see, we have our Fibonacci function, main, run, and then several of these other functions that were specified in the NM, the list of the symbols that we showed earlier. Okay, and what you see here in the brackets are is the number of instructions. Okay, so we can see here that really we don't really care about these functions right here, and we're probably targeting these three functions in our module, which are defined in the parallel overhead.cpp file. Okay, so let's switch this command line argument to print instrumented. Okay, so as you can see, main is always instrumented, so that's actually just ignored here. That's implicitly instrumented. But you can see we only have run and this uniform and distribution in our list of functions that are instrumented. That's because by default, since the Fibonacci function only has 20 instructions here, the default number of instructions excludes it. So we can include that by passing the -i flag, and let's set the -i to 16. Okay, now you see that Fibonacci, or the Fibonacci function here, is also included along with the destructor for a vector. If you want to specifically include functions, you can use the -i function, and you can see that based on the heuristics, Fibonacci was included because we specified it specifically. And if we want, we can also include that vector destructor for the same result. An alternative we could also exclude the vector, and therefore basically instrument anything with 16 or more instructions, but then we're specifically excluding this regular expression pattern, which matches our vector function. Let's talk about why the functions that are instrumented matter. So if you're not familiar with a Fibonacci function looks like this. It is a recursive call where if n is less than 2, you just return n. And otherwise, you call fib n minus 1 plus fib n minus 2. Okay, so this creates a very long recursive chain that scales up very easily. So say Fibonacci of 30 will have 100,000 at least function calls. So the important thing to note here is that because this is a very simple function, instrumenting this function will cause a lot of overhead. Okay, so in our examples, parallel overhead, it takes 3 arguments. The first argument is the starting value for the Fibonacci. So 30 here specifies that we start off calling fib 30. And we want to run it on 8 different threads. So that same fib 30 gets calculated independently on 8 different threads. And we're just going to run 1 iteration. And we're going to time that and see how long that it takes. As you can see, it takes about 0.3 seconds with no profiling overhead. So I wrote a little script here called run parallel overhead. And I'm going to do the instrumentation for parallel overhead with the default heuristics with respect to the number of instructions. I'm going to name that parallel overhead inst.0. Then I'm going to create a parallel overhead inst.1, and I'm going to reduce the number of instructions down to 16, which will cause the Fibonacci function to be included in the instrumentation. So once we run these 2 commands, we will then run our instrumented executable with a Fibonacci of 30 run on 8 threads with just 1 iteration. Okay, and we will do the exact same for Fibonacci inst of 1. Remember, the difference between these 2 is Fibonacci inst.1 has instrumentation within each one of those Fibonacci calls. So we'll end up calling Fibonacci instrumentation around Fibonacci hundreds of thousands of times in inst.1, which is a very small function relative to the runtime. So let's look at this output. Okay, as you can see, we ran this first one. It only instrumented the run function and a uniform distribution, whereas in our second one it also included Fibonacci and that vector destructor. Okay, when we ran inst.0 with these args, you can see that it only took about 0.1 plus a little more seconds of wall clock time to profile that output. Now, when we ran inst.1, it actually took over 8 seconds. So the instrumentation within Fibonacci bloated the runtime. And as you can see here, it's still actually taking quite a bit of time to write the Perfetto output, and the Perfetto output is almost a gigabyte in size, whereas in the original we had only about 10 kilobytes of output. Let's look at the high-level profile for Temery for the first one. And you can see that for the most part we have main, we have the pthread barrier wait called, we have our run function, in addition to that uniform int distribution. If we look at the output from parallel overhead in stop 1, you can see that we have these huge long recursive call chains with significant call counts. Thus, the moral of the story is the default settings within Omnitrace, so the default heuristics with regard to instruction count are kind of designed to make sure that Omnitrace doesn't have too much overhead when you're profiling. You can adjust it by various options, but in general, the default settings should give you a detailed enough profile, and if you're not seeing the level of detail that you want, then you can adjust these settings.